Thanks for organizing an in-person conference. So, I want to take my mask off, but I feel uncomfortable taking my mask off because I'm teaching with a mask on, so I don't know what to do. Okay. Is this email some announcement or something?
Yeah. Please stay to the other side of that. We're recording the talk, so.
Oh, okay, so stay. Okay, very good. All right, so this talk, I'm going to try to make into a story because I think most people here are probably not familiar with some of the things I'm going to do. So try to make this into a kind of a story or a play. And it has like three main characters, and then I'm going to describe relationships between these three main characters, and hopefully something interesting will come out. I'm not sure I'm going to get to the end of what I wanted to say, which is an application of some of the results, but we'll see. So let me start with the characters here. So of course the first character is groupoids, but in this talk they are Lie groupoids. And I think anyone that gives a talk in groupoids uses his own notation, so my notation is slightly different from the notations in the previous talk. And so in my, I use source and T for source and target, S and T. And unit map is U, and the inverse map is I. And so that's the first character. The second character is the infinitesimal version, Lie algebroids. So those are, I have a vector bundle, A. And by the way, maybe I should write here. So usually I'm going to use a G for the arrows and an M for the objects. So these maps go like that. And then the algebroid, so I have a vector bundle over M, and it will come with a bracket on the space of sections. And it comes also with a bundle map from A to the tangent bundle of the base. And then there is a third character in this story, which is locally groupoids. So loosely speaking, these are just like groupoids, but the multiplication is only defined locally. So I'm going to use a G, but a usual capital Latin G for a local groupoid. And it will have similarly maps. So you have the unit, and you have the inversion. But now multiplication, so here multiplication was defined for any pair of composable arrows. Now multiplication is defined only on an open set. And the point is that this open set has to, so it's an open set still of composable, so of arrows that have the source and the target match, but they are only defined if one of them is sufficiently small. So this open set, it's a neighborhood of M times G, the joint union with G times M. Okay, so these are my main characters here. There is one little detail, which is actually not so little, about the associativity. So because this multiplication is only defined locally, the associativity here that I will use, it's called 3 associativity. And it simply says that if I have the 3 arrows G, H, and K, and both sides are defined, they are equal. Now, this thing about both sides being defined then they are equal is a bit different than saying if one side is defined, then the other side is defined and they are equal. And it makes a huge difference to say the two different things. So let me spend just a little time in that. So, let's see here. Suppose you look at associativity for 4 arrows. So let's write the possibilities, starting, say, with this. Then if I move one parenthesis, I would get something like this. Or I could move the other way around and get something like this. And now I could further move this, and I would get something like this. And here I could further move, and I would get something like this. So we have this pentagon with the 5 possibilities. And you see what happens is because multiplication is locally defined, maybe this is defined, this is defined, but maybe this is not. So you cannot conclude from 3 associativity that 4 associativity holds. From this version. From the other version, if one side is defined, the other side is defined, that they are equal, you would conclude that 4 associativity would hold. Okay? So 3 associativity does not imply 4 associativity, and so on. So in general, note n associativity does not imply n plus 1 associativity. Okay? By the way, there will going to be many associativities written in this way. I hope no one gets offended. Okay. All right, so these are my 3 characters. And they will have some relationships. So let me put here a diagram. So I'll write here a diagram. The algebroids. Groupoids. And local groupoids. Of course, a Lie groupoid is an example of a local Lie groupoid, but for this purpose, I prefer to keep them distinct. So, what are the relationships? So first we have differentiating functors from Lie groupoids and from local Lie groupoids. I'll just write here a D. So briefly, it's just the same construction that when you go from a Lie group to a Lie algebra. So if I have, say, let's call this differentiation. If I have a G, I will obtain these data. So again, here there are various conventions. In my conventions, I take the tangent to the T fibers along the identity, along the unit. So that's my vector bundle. And then sections of this vector bundle can be identified with left invariant vector fields on the groupoid, and therefore we have a bracket. The bracket of left invariant vector field is left invariant vector field. You get a bracket. And we haven't used the source map in this, and in fact the anchor is the differential of the source map restricted to this thing. So that's the differentiation functor. And this makes sense. You can do this both for Lie groupoids and for local Lie groupoids. That's fine. Maybe more interesting is the integration functor. So integration So the first one, we start with the algebroid. We're going to associate with it a Lie groupoid. In fact, it's not quite true, but almost true. So I'm going to get something I will call G of A. This G of A is obtained as follows. You take something called A paths. I'll say in a second what that is. And you mod out by A path homotopy. So you can think of this as some kind of homotopy integration of A. So what are these A paths? So these A paths, explicitly, they are just paths in A. So I'm going to use I systematically for the interval 0, 1. So they are just paths in A. So because they are paths in A is a vector bundle, they cover a base path, which I usually call gamma index A. And not just any path in A, but they have to satisfy this additional condition that if you apply the anchor to this A path, now you get a path of tangent vectors, and that has to be the derivative of the base path. Now, it turns out that this is actually equivalent to say that if you think of this as a bundle map from the tangent of the interval to A, so I'll call it A T dt, so this is a bundle map covering my base path. This is a Lie algebroid morphism. So A paths, you should think of them as Lie algebroid morphisms from the tangent of the interval to A. And now you probably can guess what is A homotopy, or A path homotopy. They are, so I'll skip this part, and I'll just say that they are algebroid morphisms from the tangent of the square to A. And so, if you think of them, what this really is here, this will be a map that will have a component A of T epsilon dt, and then another component B of T epsilon. The epsilon, and the fact that this is a Lie algebroid morphism is translated into some differential equations for A and B, which I won't write. And then we want this to be an A path homotopy, so there are some boundary conditions. So if this is an A path homotopy between A paths A0 and A1, then here the boundary conditions will say that A of T at epsilon 0 is A0, A of T at epsilon 1 is A1, and then the fixing the endpoints, because we are working kind of with the derivatives, it means that these B's vanish at T equals 0 and at T equals 1. So, working in this way and defining multiplication to be concatenation of paths, of A paths, you do get the groupoid over M. You can choose a nice topology in the space of A paths. Say you can choose the C1 topology, and you put the quotient topology on this, and this is a topological groupoid. So this integration functor goes to something bigger, which is topological groupoid. Okay. Now, there is a version of this integration functor where you don't take any A paths in A, you take a small open set containing the zero section of A, and you work with that, And then you restrict a path homotopy to that to lie on that open set, and then what you get is a local Lie groupoid. And now it's really a Lie groupoid. So there is a version of this construction that gives you an arrow here. So let's call this integration. Okay. So sometimes this is called a Weinstein groupoid. Okay, so there are some relations between our characters. There is one more relation that I want to describe, which is from here to here. From locally groupoids to Lie groupoids. To groupoids. So if I start with a local Lie groupoid, I can attempt to make it into a global groupoid. So this is my, let's call this, we'll call this the associative completion. So what is this? Well, we're going to take words. We'll call this words. In this groupoid model, some obvious equivalence relations. So here words. So these are my words, okay? And now remember that because we are in a local Lie groupoid, it doesn't mean we can multiply any arrows, only some arrows. And so this equivalence relation is going to be the equivalence relation generated by identifying words that can be contracted into successive elements. So I declare these to be equivalent if indeed I can multiply them, which is not always the case. Okay, this generates an equivalence relation. That's the equivalence relation there. And now this is an honest groupoid with concatenation of words. And again, there is, here you can put an obvious topology by taking the topology you started in G, and so you can put the quotient topology there. This becomes actually a topological groupoid. So there is an arrow that, in fact, again, doesn't land on Lie groupoids, it lands on topological groupoids. So that's the other relationship that was missing there. So, I mean, I'm not emphasizing that, but all these things are really phantoms. These are also acts between, if I start with, say, a morphism of Lie groupoids, there is going to be an arrow between, a morphism between the associative completions. Okay? These are really phantoms. All those. Okay, now there is an obvious mismatch here, which is that this lands in topological, not in Lie. So you would like to know, when does the associative completion is a Lie groupoid? Or if I give you an algebroid, when is the Weinstein groupoid a Lie algebroid, not just a topological groupoid, not just a topological groupoid. A Lie groupoid, not just a topological. Sorry. Okay, so that's where these titles these words in the title of the talk come in: integrability and associativity. So let me say about that. So let me start first by discussing this integration from algebroids to groupoid. So that's something that it's very old, that people know that not every algebroid comes from a Lie groupoid. And so at some point, people wanted to understand what was the obstructions to have a Lie groupoid associated with a Lie algebroid. And eventually, after many years, a complete theory was developed. And so let me just give you a very quick, summary of that. So to describe the obstructions, let me do the following thing. So given an algebroid, so at each point of my base, I have the isotropy, what's called the isotropy Lie algebra, which is simply the kernel of the anchor map. So the bracket on sections restricts to a bracket on this vector space, makes this into a Lie algebra. And my definition of a path is still here. You see that if I have a path that takes values in the kernel of the anchor, this thing is automatically satisfied because the base is just a point. So if I take a V in here, can view it as a constant a path in particular. Okay? The a path, but for every t between 0 and 1 is equal to v. That's it. So because of that, we can define some groups called monogramming groups. At each point x, there is a monogramming group, and the definition is very simple. These are an element in the isotropy Lie algebra, which when viewed as a path, it's a path homotopic to the constant 0 path at x. Okay? So this is a abelian subgroup of the isotropy. And we can take the union of these monogramming groups. So now I have something inside A. And the theorem, so I guess I can now, well, maybe I'll put it here. Except that I'm going to keep this statement. It's too bad I cannot use that part. Okay, I guess this goes away. So this is by my scanning itself. This is very old. This is 02 or 03 or whatever. And it says the following for the algebroid, the following are equivalent. There exists some groupoid, some Lie groupoid, with Lie algebroid A, so that it differentiates to A. 2, these groupoids that we construct, this topological groupoid that we constructed, is a Lie groupoid. So here one should be very specific, a bit more specific about the smooth structure, but the idea is that you have this space of A paths, it's a Banach manifold, and the point is that the quotient by homotopy is a Lie groupoid with the smooth structure induced from this Banach manifold if and only if the other conditions hold. And 3, this is uniformly discrete. So what that means is that there exists an open containing the zero section such that the only elements in this open intersecting NA is the zero section. So these groups are not just discrete for each x. When you vary the x, they stay away from 0. So that gives you a satisfactory answer for this thing. It's also that the fact that these things are computable. These are computable. But I don't want to talk about that because we don't have time for you compute. Okay? All right, so that's about what is the subset here that lands in there. So what is the subset here that lands in Lie? Well, the first answer is provided by a groupoid version of the very old theorem in Lie theory due to Malsev. So let me take that result as Malsev theorem for groupoids, for Lie groupoids. So, I mean, there is in some sense this is due to Van Est, but there is also a paper that I wrote with a student of mine where we actually give a detailed proof of this, which you cannot find in Van Est. This is from 2 years ago or something. And so this theorem says something very simple. It says that a local Lie groupoid is enlargeable to a Lie groupoid if and only if it is globally associative. And this reminds me, I forgot to say something about this result here. So in proving this result, you also give a construction for any Lie algebroid of a local Lie groupoid. Okay. It's using the same kind of techniques. So that's actually how you construct this thing. Anyway, so what do I mean here by enlargeable? Well, what I mean is that a local Lie groupoid can be viewed as a neighborhood of the units in some Lie groupoid if and only if associativity holds for every n. That's what this means here. So let's see. N associativity holds for all n. Now, something that I could have also mentioned before is that if you start with a local Lie groupoid, we only assume 3 associativity, it's possible to make it smaller, to restrict this local Lie groupoid, to make it n associative for any n that you wish. But in general, it's not possible to make it associative for every n. Okay? And this business about restricting is kind of important because you only want to work with locally groupoids as germs, not as honest objects. Anyway. Now, this doesn't quite solve completely this issue because here I said I start with a locally groupoid and I construct a topological groupoid by doing this associative completion, by taking these words, mulling out by this equivalence relation. So when is that a Lie groupoid? And in fact, to prove this result, you have to go through that, which is not done in Van Est. Anyway. So let me say how you're going to do that. Suppose I have a local Lie groupoid. Let's fix a point in M. And then I have Gx, the arrows that start and end at x. Because this is a local Lie groupoid, this is not a group, but it's a local Lie group. And we're going to define the associators at x. Let me write this notation like this. To be the elements in these isotropy local Lie group, I call it just isotropy group, which are equivalent to the identity at x. This is this equivalence relation generated by these words. So what does this mean? It means that I can start, think of this as a word with one letter. I start expanding it, and then I start contracting it, maybe expanding it, contracting, and I end up at the identity. Okay? So this is contained in Gx. And I want to say something more here. Maybe I'll just write second theorem. So it's in the same paper as this one. A paper, whatever. You can find it in the archive too. In a paper whose title is either these or a combination of these. I don't know. So the second theorem, maybe someone can guess it. Can anyone guess it, what it says? So I'm taking the union of all these associators, as I did for the moment. So I hope this makes an analogy between what's going on there and what's going on here. And again, here uniformly discrete is what you guess, right? There is a neighborhood of the units whose intersection with this consists only of the identities. Okay. And then Malsev's theorem follows from this because if it's globally associative, all these things are just stripped, just consist of the units. So that tells you which are the local Lie groupoids that you are landing in there. Okay. It also asks for a relationship between these two things. They should be related. And indeed, they are related. because we have the following result here. Same paper, so I won't bother to write. There exists for any groupoid. Okay, there are some assumptions on the fibers and stuff like that. It's by passing to germs, you can think this is for any. Remember, locally groupoids have algebroids, so can be differentiated. So there is an open A containing the identity such that if you look at so remember, these were some subgroups inside the isotropy, inside A. So I can take the usual exponential map for the, if you want, for this group. And so what I'm saying is that this equals this for every x. So this is giving you an interpretation for these monogramming groups, what they are and how they are measuring this failure in integrability in terms of these locally groupoids. And so that's kind of like completes the picture of that diagram. All right, so how am I doing with time? How much time do I have left?
You have a little under 15 minutes.
Very good. So then I can explain this application. So this maybe sounds a bit too exoteric, I don't know. So let me give you an application of these things to something. So maybe some of you are familiar with Kontsevich work on deformation quantization and the formality theorem. So in Kontsevich, he looks at the question of existence of formal star products, and he shows that that's always the case by using the formality conjecture theorem. And what I want to do is to look at not at formal star products, but the non-formal star products. So all this non-formal deformation quantization. So this is a, you see, when you are working with, I mean, Kontsevich work is amazing, it's beautiful, but it's formal. So in that sense, it's a bit unsatisfactory. You would like to produce things that are not formal. You would like to produce honest star product. Star product, you think, is just a deformation of the usual product of functions. So, I mean, there are many works where people construct non-formal deformation quantizations and non-formal star products, but it's like each class or each example is its own thing. And there is really no general theory about non-formal deformation quantization or non-formal star products. There are only like pieces. And so at some point, what I start looking at with Alejandro Cabrera in Brazil is that the question of obstructions. So instead of constructing, which is very hard, we are saying, okay, assume that there exists one. What can you deduce from that? And the funny thing is that you can use these local these things that I explained about locally groupoids and relationship with associativity to find obstruction. Which there were no, I mean, by the way, this is unpublished work, so take that as you wish. Not, but there are no known obstructions to deformation quantization, at least that I know of, non-formal deformation. While the formal problem is unobstructed. So what do I mean by a non-formal deformation quantization? So let me start with that. So a star product of Fourier integral type so this is going to be a Panin operator is going to depend on some parameter h. That's the deformation parameter, which is taking some pair of L2 functions and giving you a new function. But here, being a Fourier integral type, what it means is that the kernel of this operator is a semi-classical Fourier integral distribution. And now to be a star product, it has to satisfy a few properties. Well, first of all, it should deform the usual product. So you should start with something like that, but here only for smooth, say, functions of compact support. Oh, and maybe I should, before saying something, I'm going to say something more about. So a priori here, it looks like I'm only allowing functions that are independent of h. But in fact, we are going to allow this to act on functions that depend also on the parameter h. Okay? So maybe I'll make a separate note here. Note. But the thing is, I will not write in general the age, and we will assume that this norm in L2 of this family is bound. So here in this first equation, when I write f and g in here, they are independent. They do not depend on h. Okay, so they deform the usual product. The second thing is that we should have some associativity. Let's write this. Okay, and that I see. F1, F2, F1, F2. It's better. Let's write maybe this way. This is in L2. This here is also in L2. And here I'm allowing for age-dependent functions. Okay. So that's the associativity. Third, we need an identity. So I'll just write this in this way. This way. One, again in L2, and again H dependent. Otherwise, this will follow from 1. We were H independent. Well, except that 1 does not have compact support. But don't worry about that. There is a way of writing this. Let me just not lose time with that. And the final thing is that this should be micro-local continuums. So star H is micro-local continuous. So, I mean, what I mean by that is that there exists some open. Okay, let's forget about the open and just write that something that, or maybe, yeah. No, I think I need to, excuse me. So given an open in the cotangent bundle containing the identity, there exists another open in the cotangent bundle containing the identity, such that if the wavefront, the semi-classical wavefront sets of F1 and F2 are contained in W, then the semi-classical wavefront set of the star product is contained in V. Now, if you don't know what is the semi-classical wavefront set, I won't have time to explain, but basically it's a way of, so you have to take Fourier transform, you look in phase space, and you are looking at the points in phase space where this function in terms of age, when age goes to 0, has something left. Okay, that's basically it. All right, so this looks like completely disconnected from my previous first part of the talk. So what is the connection? Well, whenever you have an operator of Fourier integral type, there is a Lagrangian submanifold behind it. And here is not associated. Lagrangian submanifold. Lambda contained. It's contained in where? Well, because this kernel is really in n times n times n. This is contained in the cotangent bundle of n, cotangent bundle of n, cotangent bundle of n. And we change the sign of the symplectic form, the canonical symplectic form of the cotangent bundle. So there is a Lagrangian submanifold behind this. And now the theorem, as much as you can call a theorem for work in progress, says that this Lagrangian submanifold is the graph of a local symplectic groupoid. If you don't care about the symplectic part, no worries. But moreover, this is globally associative. And 1, 2. If you look at the semi-classical approximation, so that means you look at the star commutator, you divide by h, and you want to let like h go to 0 if you want, but this defines Poisson bracket. So in fact, the statement is that this difference is O of h for some Poisson bracket. on the space of smooth functions on M. And this local symplectic groupoid integrates this Poisson bracket. So whatever that means. So the Poisson bracket defines the Lie algebroid. This groupoid integrates the Lie algebroid defined by the Poisson bracket. So I'll finish by saying now, what are the obstructions? Well, the obstruction is that if you start with a Poisson manifold and you want to find a star product deforming it, that Poisson manifold has to be integrable to a symplectic groupoid. And we do know how to describe these even geometrically in terms of symplectically and stuff like that. But in terms of these monogramming groups, as I explained in this special case. So that's it. Sorry for running away with the time.
Does anybody have any questions for Rui?
Yeah.
Where does H live? Is there some?
H is a parameter living in fact, in the open interval 0, 1, if you want, or if you want H0 for a fixed H0. And so what you are doing here is you want to look at what happens when H goes to 0, right? When H goes to 0, this is deforming the usual product. What we are saying is any reasonable definition, because, so if you look at any definition of non-formal deformation, they will satisfy these axioms, in fact. They will be of Fourier integral type. And any reasonable definition of such thing gives rise, in first order in H, to a Poisson bracket, always. So that's also true in the formal setup. If you start with a formal star product, so some H star that depends on the power series in H, the first term in the power series is also an honest Poisson bracket. And so that's called the semi-classical approximation. And yeah, and now you see that there are these obstructions to deforming, to finding a star product in the direction of a given Poisson bracket. You can only find in the direction of Poisson brackets that are integrable. That's what the theorem says.
Any other questions?
What makes these star products non-formal, or the deformation quantization non-formal?
Well, because it's an operator. You're associating to a pair of functions. In the conserved stuff, you're giving a pair of functions and you're giving a power series in H.
Okay.
Not an honest function,
Okay.
which in general doesn't converge. This power series, and you cannot look for power series that converges, because you can always choose, given any star product given by a formal power series, you can always choose functions which have derivatives which will make the power series diverge. So you cannot look at convergence in that sense. So what you have to do is to look at things that in some sense are operations that in some sense depend on the local behavior of f and g. And so the natural thing is to look at Fourier integral operators.
Thanks.
Any other questions? Let's thank the speaker again.